Hi, this is my video number 3 for mth3101. Right. So now I'll talk on the change of variable in multiple integral. Change of variable is not well focused. Just a minute. All right. Change of variable in multiple integral. Specifically, we talk on the double integral. Okay, so as a review, or just to recall what we have done, you have done basically in one variable case, when we do the change of variable. So what happened actually from the integral? So in one variable case, in one variable, so we integrate from a to b fx dx. So if you cannot integrate that directly, normally we change the variable, right? So for example, x function of u, all right, and then what happened here is that those integral becomes we integrate with the new limit there. Let's say those new limits c and d, yeah. And then the function, we change each of x with those function of u, that, and we differentiate dx to obtain in term of du, so that we have g prime u du. So that's what happened in the single variable case, yeah, where in this case x is equal to gu, and our a is actually equal to g of c, and b is equal to g of d. Okay, so for the double integral, the example that I've given in my previous lecture when we deal with a polar coordinates, if you remember, we do x equal to r. So this is in double integral. Double integral. We do the change of coordinate x r cos theta, y r sin theta. All right. And what happened to dA or dx dy or dy dx? We have some r here, as you call it, as the Jacobian of the transformation, dr d theta. So our integral over the region D, say f xy dA, we transform into a polar coordinates with, of course, I would write this as a d in polar coordinate or polar coordinate system. Let's say dr theta. So fxy, now fx with r cos theta, r sin theta for y, and dA becomes r dr d theta. So this is example of change of variable in double integral. So what actually happened? Actually, we do a kind of transformation, yeah, a kind of transformation from plane, say uv, to plane xy. So this, let's say we have a region here, and we transform to a new region here, that under some kind of transformation, let's call that transformation t. So if those transformation is 1-to-1, then you can transform from UV plane to xy plane as well as xy plane to uv plane. That for the case of 1 to 1. So for the case of 1 to 1, we can find inverse of those things. Okay, so this kind of transformation, let's say we call t, we transform from uv to xy, where x we write in terms of function u and v, and y we write in terms of function u and v. So those transformation. Okay. Let me give you example of how this transformation work. We haven't deal with the double integral yet, just the transformation. Now we consider the let's say our transformation is defined as transformation. Okay. We define our transformation as x equal to u squared minus v squared. Alright, so it's not well focused, just alright, I think that's better. And y u to uv. So we want to find the image of the square, given by this as uv such that u 0 to 1 and v 0 to 1. Okay, so if we sketch the region S, which is under UV coordinate system, so you have UV, alright, where U from 0 to 1, V from 0 to 1, so we have 0 to 1 here, V 0 to 1, so we have basically, this is our region S. Now we want to transform this into xy. So what does the region in those region look like in a xy plane? So in this case, we need to consider each of these edges. Each of these edges. So let's consider this as S1. Let's consider this as 2. Let's consider this as 3. And consider this as 4. So note that the equation here, this is v equal to 0, this one, and v from 0 to 1, u from 0 to 1, and for this is u equal to 1. So let me write those things. For S1, we have v equal to 0 and u from 0 to 1. Okay, for S2, what we have, u equal to 1 and v from 0 to 1. That, and for S3, we have v equal to 1 and u from 0 to 1. And S4, u equal to 0 and v from 0 to 1. So this is the region S. Each of these edges of S is defined here, like that. Now we are going to transform each of these edges into xy plane according to that transformation. Okay. Now, in order to do that, we need to consider each of those edges separately. So let's consider first S1. Yeah. Let's consider S1. For S1, we know that V is equal to 0 and U in between 0 and 1. If we substitute this from our transformation given here, so what we have, X is equal to U squared, alright, and Y equal to 0. Y equal to 0 because V equal to 0. So we have V equal to 0, that one you got X equal to U squared, and Y, U is 0, then Y equal to, V is 0, then Y equal to 0. So we have X 0 and 1. And the limit for X, since U from 0 to 1, if you substitute in there, so what we got, X is still 0 to 1. So we have X between 0 and 1. So from there you can see Sy, we transform that. Yeah, let me plot it here. This is on XY plane. So you have X from 0 to 1. Yeah, from 0 to 1. So from here, let's make it a little bit longer. From here, this is 0, 0 to 1 here, say. This is 1. So those S1 transform into this one here. So let's call this as a S1 prime after transformation. Okay. So those line transform into. So I write here this. I put it as a S1 prime. That. Now consider S2. S2 here. This S2. Where S2, our U is defined as U equal to 1 and V from 0 to 1. So what happened? We will have, if you substitute into the U equal to 1, so we have X equal to 1 minus V squared. So we have X equal to 1 minus V squared, and Y equal to 2V. Y equal to 2V. Alright? Then if you eliminate V, because here you have V, here you have V. Remember that when we do transformation on XY plane, we shouldn't have any UV anymore. Yeah, okay? We should have no UV anymore. Should be X and Y. So in this case, we still have UV, but now we need to eliminate V. Okay? If you eliminate V, so what we have, therefore we have X is equal to, you can substitute this. This is V equal to Y over 2. Put it there, so you have Y 1 minus Y squared over 4. Where X between, your X between 0 and 1, because V is 0 to 1, you substitute there, you still got 0 to 1. So X 0 to 1. Okay? V is 0 to 1. When V is 0, you got X equal to 1. When V equal to 1, you got X equal to 0. So that's why we have those. So you can see from here, this is a parabola. Right? This is a parabola. So 1 minus Y squared over 4. So 1 minus Y squared, you just have 4 there. So on the X plane, you have when Y is 0, X equal to 1 here. Alright. When X is 0, you got Y plus minus 2. So of course 1 here and 1 here. So we just consider the upper parts. So which means somewhere here. Correct? Y x 0. Yeah. So we have Y squared equal to X equal to 0. So we have 1 here, 4, correct? I think that's correct. Okay, so we have y equal to plus minus 2. So we have 2 and negative 2 down here. Alright, so if you consider only the positive part there, then we have those. This is S, let's call that as S2 prime. Okay, so I put this as a S2 prime. Then we consider the third axis here, S3, that one. Let me use for S3, we have here, we define V equal to 1 and U from 0 to 1. 0 to 1. We do the same thing, substitute V into that. So what will happen? We have X equal to we have V equal to 1, so we have U squared minus 1. Alright, and Y equal to 2U. Alright, now if we eliminate U, so what we have is that X equal to Y squared over 4 minus 1, where X, you can see a 0, U from 0 to 1, so you can substitute that when U is 0, X equal to minus 1, so X is minus 1. When U equal to 1, you got X to 0. So we have X from minus 1 to 0. So this is again a parabola with opening to the right side. So we have those 1 minus 1 is here, so we have again a parabola there. Okay, so this is your S3 prime. So I call this as a S3 prime. Now then you need to consider for S4. For S4 we have U equal to 0. U equal to 0 and V from 0 to 1. Okay, so substitute again into our transformation. X equal to minus V squared and Y equal to 0. Y equal to 0, this is on x-axis, and X, if you substitute V 0 to 0 and 1 into here, so we have X between minus 1 and 0. So Y 0, X from minus 1 to 0. Come back to our diagram here. So we have, this is our S4 prime. Okay, this S4 prime. So now we can see that under that transformation, X U squared minus V squared and Y equal to 2UV. So basically this is our function that we define as X as a function of UV. This is our function that we define as Y equal to XH, for example, H U UV. We transform those things. So what happened is that we transform from a square in UV coordinate system, UV coordinate system, into this kind of shape in XY coordinate system. Okay, so I hope you get this thing. So in terms of integration, if you want to talk on the integration, if you consider these two regions here, these two regions, that and that, which one is much easier to integrate for double integration? Surely this one, alright? Surely that one, because this is, we integrate just on the square. So the integration of x and y is just 0 to 1, 0 to 1. Integration respect to u and v, just 0 to 1, 0 to 1. As compared to xy plane, you need to write in terms of you have x squared here and everything, so it's not as easy as uv plane. Okay, let's consider another example. Try to see another example. Okay. So let's say the region in xy plane bounded by on xy plane, so region bounded by x plus y equal to 6 and x minus y equal to 2 and y equal to 0. It is not difficult, of course, to sketch those region bounded by those equation. So on xy plane, xy, okay, and then we want to use the transformation. Our transformation here is that transformation that x equal to u plus v, y equal to u minus v. So let's see how the region look like. First, on the xy plane, given by that boundary, so you can x plus y equal to 6. So you basically you have this equation, this line. All right, here 6, here 6. This is x plus y equal to 6, and then you have x minus y equal to 2, so y equal to x minus 2. So we have y equal to x minus 2. We need a little bit lower, so we have something like that. Okay, so this is x minus 2 minus y equal to 2 and y equal to 0 here. So our region is that. Alright, so this is our, let's call this region, give it name, let's say R. Now we want to transform that region into xy, uv under that transformation. What happened here? So again, we need to consider each of those lines one by one. So let's consider this as let's say R1, let's say that one R2, let's say here R3. Okay, so what we have, here, so for R1, we have y equal to 0, and x between what? Here is 6, here is 2, here is 2. Right? So x from 2 to 6. So what happened to that transformation when we have y equal to 0? Yeah, y equal to 0. So we have u minus v equal to 0, and for x okay, so we have u equal to v, and x from 2 to 6. So x from 2 to 6. From there you can solve those things. Then on uv plane we have, this is u, this is v, then we have u equal to v. So we have that u equal to v. Okay, and then if you consider others, let's say consider R2, your R2 line is given as x plus y equal to 6, right? And that one is and x from that point to here. So with those x plus 1 and x minus y, so what happened now? X plus y equal to 6. So you have our transformation here. If we do x plus y, that will give you x plus y, so that you have 2u, right? So we have 2u. This is equal to 6 here. That's equal to 6. So therefore you have u equal to 3. So we have that line. So this is u equal to 3. So let's say this is R1 prime. This is, let's say, R2 prime. And then for R3, we have R3 is that R3 x minus y equal to 2. If you look at our transformation here, x minus y, what will happen? X minus y, that give you, so x minus y, you cancel out, so we got 2v, right? That equal to 2. Then just substitute here, yeah, x minus y. So right hand side you have u minus u, you got 0. V minus negative v, you got 2v. This is equal to 2. So we have v equal to 1. So we have the equation v equal to 1 somewhere, let's say somewhere here. That, so this is your R3 prime. So this is 1, this is 3, and this is v equal to 1. So our region is that. This is the region under a new transformation on UV plane. Okay, so hope you can understand those things. Now, of course, in the notes you have some exercise there. I think you can have a look on those exercise. Now, if you look at this transformation, yeah, from even from here, this is our first example of the transformation that given. Now, the area for this and the area for this is not the same. Yeah, the area is not the same. So in order to make it the same, that's appear the term what we call as the Jacobian of the transformation. Okay, so that's the idea of the Jacobian of the transformation. So that's why for the let me write here, for the polar coordinates, yeah, for the polar coordinate, we have under xy plane. Let's say this is our region in xy plane, for example, and if you pick up one of the a piece of it, yeah, very small. This is dx. This is dy into r and theta, yeah, r and theta. So r, we have a circle, we have r and theta, and this small part here we transform into small part here. That, okay. So for the area of those, we have dx, dy. Okay. Now we transform into now dr, d theta. This will give you the area of those small piece, and this part also give you the area of the small piece, but they are different. To make it equivalent, we need that what we call those Jacobian. This is the Jacobian of the transformation. Jacobian of the transformation. Okay, that's we call it as a Jacobian of the transformation. So having J there, so we have then we have dx dy is equal to, in this case, as I have explained in my previous lecture, that this j is equal to r dr d theta. Okay, now let us look at the more general case of the Jacobian. So look at the definition. Yeah, the Jacobian of the transformation. Jacobian of the transformation T given by x g of uv y h of uv, this is our transformation, is that del xy del uv, this is given as I can write this as a xu xv yu yv. Okay, you can just find the determination of the find the determinant of the matrix 2 by 2 matrix. Okay, so this is the Jacobian of the transformation. Now let's look at the change of variable in double integral. For the double integrals, it's a change of variable in double integral. Yeah. Change of variable in double integral. So we have I have mentioned that from uv, or from xy, we transform into uv. Okay, and small area here on xy plane, we transform into the area here under uv and plus those Jacobian. So we have dx dy, that will give you du dv some Jacobian there. Okay, we apply that. So the integral over the region R, this is our whole region here, this is our region on UV plane. Okay, we under this the region R, this is here is R, here let's call this is R prime. That region we call it as R prime. So now f xy dA, this is equal to the integral over our new region under those transformation R prime. Now f, our x is given here g of function uv and y function of uv. So I can write this as a x function of uv, y as a function of uv. Okay, and here the Jacobian is given as the del xy over del uv du dv. So remember this. Okay, you don't have to worry about this. It's difficult to memorize. No, it is just j, and you know what j is. I have explained to you what j is, and it is the absolute of those things. Okay, of course, a simple example is in polar coordinate that we have discussed, that we have x equal to r cos theta, y equal to r sine theta. If you do this, we find the Jacobian is given as follow this. So we have xr x theta yr y theta, that give you xr is cos theta, x theta is negative r sine theta. Here we have yr, we got sine theta, and y theta is r cos theta. Alright, and everything there, that give you r. Okay, other example I can we have in your notes there, the example. Let's say x equal to u squared minus v squared, y equal to 2uv. Okay, we use that change of variable to evaluate this integral over r y dA. And we know that, I think we have done just now those things. Let me, where is it? I think I have sketched those things. Try to find, okay. No, okay, this one here. This one here. Alright? So we want to evaluate integral over that region. So it is not easy, and then we do the transformation. Such transformation will transform from that region with curved boundary into the just a square, much easier. Okay, so having done this, and we know that from that equation here and here, so you have what this is. This is that give you y squared equal to what? 4 minus 4x. Yeah, 4 minus 4x. This one y squared equal to 4 plus 4x. Okay, so that one y squared 4 minus 4x. This one y squared 4 plus 4x. Okay, now we know that those region R, as I showed you just now, our region R now bounded by y squared equal to 4 minus 4x and y squared equal to 4 plus 4x. And under that transformation, this region transform into say R prime. Our R prime is u 0 to 1 and v 0 to 1. Okay, all this have been discussed in that example. Okay, now you need to find the Jacobian of the transformation. The Jacobian of the transformation is that del Jacobian is that del xy del uv. So this is xu xv yu yv. Okay, so this is so xu, yeah, for this. Okay, so you have xu is 2u, xv is a minus 2v, and then yu, you got 2v, and then you have 2u. So that gives you 4u squared plus 4v squared. 4v squared. This is positive, so if you take the absolute of this, you still got the same thing there. So therefore, to evaluate those integral, evaluate those integral over r, y dA, we can write this as a integrate into a new region r prime. Our y is equal to 2uv, okay? Y equal to 2uv. So you just substitute there. This is 2uv. And our dA, which is dx dy, we have the Jacobian 4u squared plus 4v squared. This is your Jacobian. And du dv. That's all. Okay, so that's make our life much easier. Your u from 0 to 1, your v from 0 to 1. This is you just simplify those things. What you have is that 2, so you have 8. Okay, I can take out 8, put it here, just a constant. I put it outside the integral. Then you have uv, so you have u cube v plus uv cube. Okay, dv du. Okay, so again, use you can integrate this iterately. So what we have, so we have 8 over there. This is u from 0 to 1. We integrate with respect to v, so we have u cube v squared over 2. Alright. Plus this one is u v 4 over 4 du. V from 0 to 1 du. So what we have is that 8 u 0 to 1 v is 1, so u cube over 2 plus that one is u over 4 du, and v 0, that cancel out everything. So again, just integrate with respect to u. We have 8, then this one is u 4 over 8 plus u 2 over 8 from 0 to 1. So that gives you 8 1 over 8 plus 1 over 8. So your answer is, you got 2, 16, cancel out, you should get 2. Alright, so now having done that with those examples, now let me, I think better for you to do some exercise. Alright, try this for yourself. Let's say we want to evaluate those integral r where the integral is x e to x plus y over x minus y dA, where your r is given by trapezoidal, 1 0 2 0 0 minus 2 and 0 minus 1, and then the transformation is u equal to x plus y and v equal to x minus y. So remember that in this case, in the previous example, the transformation is given in terms of x a function of uv, y a function of uv. In this case, given oppositely where r as a function of x and y, v a function of x and y. So you need to be careful with that. Okay, so probably you want to sketch a little bit what r it look like. So if you sketch those things, there is yeah, so if you sketch those things, so you have x and y. So r 10 is here, say 10 here, that, and then 20 somewhere here, and 0 minus 2, 0 minus 2, so here, say here, and 0 minus 1, say here. So this is your origin. Oh, so this is your origin. I think my pen out of ink. Just a minute. So we have this is our arc. All right, so this is our arc. So can you figure out under those transformation here, this figure, how does this figure look like in UV plane? Okay, so and you can having done this, you can determine the limit of integration, and therefore you can solve this problem. Okay, so I think I stop there for this video. Then as a conclusion to what we have done in this case, that we do a transformation from xy plane to uv plane. So when we apply to the double integral, that we make our task much easier. And remember that in the transformation, we must have the what we call the Jacobian of the transformation. So with that, I thank you. See you in the next video. Bye.